I don't know. Arik likes languages, so maybe that's why.
Professor Kaplansky volunteered to record one in Georgian for the next time he got it.
Nice.
One person.
All right. Well, let me make first an announcement that again I'm out of town on Thursday. The good news is that this class is a little bit more flexible. So I'm actually going to deliver the lecture later today, and if some of you want to come, I would love it, because I don't really think it'll be a lot of fun to lecture to an empty classroom, but I will do that if I have to. So the next lecture, do you know what number we're at?
This is lecture 11.
11. So lecture 12 will be today at noon here. Okay. Well, you know it has to be here, because, yep.
The homework is due on Tuesday?
Mm-hmm.
Is it really due on Tuesday and not Thursday?
It is due on Tuesday, and you have office hours on Tuesday, so yeah. And office hours today. And yeah, last homework I hadn't given you 2 weekends, and I think this time I did give you 2 weekends, and I think that's good. So it is due Tuesday. Yeah. So yeah, please, some of you come. Otherwise, you're gonna have a very boring lecture recorded. I don't know how much enthusiasm I'll have speaking to an empty room. Right, and so what I want to do today, well, what I want to do in this lecture is prove for you a couple of interesting properties of the antipode. Okay? But so let's remind ourselves what that's about. So we have a by algebra H. And remember that we have we considered the linear functions from H to H, but we consider the input with the coalgebra structure, the output with the algebra structure, and we saw that this is an algebra with multiplication given by convolution. So we have two functions from H to H, then their product, the convolution product, is given by this. And here we're making use of both the algebra and the coalgebra structure, because by writing this in Spieler notation, we need H to have a coproduct. So that's the coalgebra structure. And then f of H1, well, f goes from here to here, so f of H1 lands here, g of H2 lands here, and we need to multiply them, and we use the algebra structure here. Okay. Now, I wanted to actually start by making a comment / warning, because this created some confusion, and very understandably so. So here's a warning. The warning is that we have two identities here. We have two identities lying around, and we use them both, and we even write them in the same equation, right? So there are two identities here. The first identity is what we call I. Okay. And I'm not writing HC, HA, so that you think of I as just the identity map from H to H. And that is the identity in here under composition. Okay? This is the identity under composition of functions. Okay. But then we have a different identity, which we saw was the composition of U and epsilon, and that's the identity in here in the algebra. Okay. Under convolution. And I asked you to check, and it's very easy to check that this really is the identity under convolution. But that's something to be careful about. And once you are careful about that, then we say that S is an antipode, but we proved last time that you can say the antipode because if it exists, is unique. It's the antipode for H. If under the convolution product, it is the two-sided inverse of this guy. Or in Fiedler notation, you know this? This is id est, which is that is in Latin. So that means that the sum over H of S of H1, H2 should be equal to U epsilon of H should be equal to the sum over H of H1 S of H2. Okay. So that is the antipode for the bialgebra if it exists, and if so, we call this. So if S exists, then that makes H into a Hopf algebra. Okay. So that's where we were last time. Are you guys happy with this? Any questions about it before we move on? Yeah?
Can I just get an education question?
Mm-hmm.
So in Hopf HCHA, I'm assuming that superscript C, superscript A means we know this as a coalgebra or this is an algebra.
Mm-hmm.
But if H is a bialgebra, why do we need to specify that? Can this be regarded as both simultaneously?
Yeah, I mean, if you remember, I showed that Hom of CA was an algebra whenever you had a coalgebra C and an algebra A. And kind of left over from that, I do it like this so that you regard this. You remember that here you only need the coalgebra structure, here you only need the algebra structure. But yeah, I mean, you might as well just drop the C and the A, and that's also a true statement.
I think you just answered that, but I wanted to clarify. So there are no maps different between those two, just in terms of what they do beyond this page.
That's right. So the elements of this are the linear functions from H to H, and the elements of this are also the linear functions from H to H. So as sets, they're the same thing.
None of them are excluded by this structure.
That's right. And I actually here I'm denoting them differently just so that you remember that here operation is composition and here the operation is convolution. But as vector spaces, they're the same thing. Okay. So that's that. And remember, we proved last time that if you have it's it's clear from this definition that if you have an antipode, it's unique, because if you have two-sided inverses, they're unique. And we made that argument last time. And what I want to do today is show some properties, some really nice properties of the antipode. So here's a proposition. In any Hopf algebra H, I have the following identities. So first, I'm going to show that, I mean, the definition of S is kind of linear. It doesn't really seem to say anything about the multiplicative structure in the algebra, but I'm going to show that S actually is compatible with the multiplicative structure, but not quite. So maybe the most optimistic thing you could hope is that what? Is that S of GH is what? S of G, S of H. Why would you guess that it's S of H, S of G? Because you saw the notes already. Good. So it turns out that this is true. Why might we anticipate that it's like this and not S of G, S of H? Or what does this formula remind you of? What is it? This should remind you of the formula for inverses in a group. And that's not just a resemblance. Remember that we showed that inverses in groups are special cases of antipodes. Okay? And therefore, it is reasonable to expect that if this is going to be multiplicative, well, it should do it backwards like inverses do. Okay? And it does. Two, S composed with a unit is the unit. Three, the co-unit composed with S is S. Something wrong? Sorry, it's epsilon. Something bothering you, Nino? Okay. And fourth, well, you might anticipate that if I'm talking about S-preserving product, unit, co-unit, then this should be something about the coproduct. So what it says is that if I take the coproduct and I compose it with H, again, what is the most optimistic thing you could hope for here? You could hope that that S is a coalgebra homomorphism. And what is that? So I'm going to write something false. Okay? Don't write this down. But if it was a coalgebra homomorphism, you would have this. Right? That's the definition of coalgebra homomorphism, that you preserve the coproduct in this way. And given that this is twisted, you might think, well, maybe this is also twisted, and it is.
Are we omitting tensor products in
Yes. 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 That's right. So if it was a coalgebra homomorphism, you would have 1 and 2 here, but this actually reverses the coordinates. So that means that S is, so 1 and 2 say that S is almost an algebra homomorphism. Actually, we call this an algebra antimorphism, or anti-homomorphism, because it just flips the product. And 3 and 4 say that S is a coalgebra antimorphism. Let me put the quotation marks here. And what do I mean by algebra antimorphism? I mean exactly this. Something that satisfies these two, a function S that satisfies these two properties is going to be an algebra antimorphism. And if it satisfies these two, it's going to be a coalgebra antimorphism.
So 4 will be an algebra antimorphism algebra.
Right, so these are the defining properties of an algebra antimorphism. Anything that satisfies those properties is called like that. Now, the proofs are kind of similar, and so what I'm going to do is just prove one for you, and I'm gonna let you fill in the details for the other ones. Okay. And maybe what I'll do, I think I'm going to try to do this over there. So I'm going to just write down the formulas that I need. So convolution product is this. And this is one of the definitions of antipode. Okay. And I think maybe I'll also write it in Sweetler notation for in case we need it. Equals the opposite equals this. Okay. Maybe I'll just write it. Okay. Something?
So start the multiplication in the algebra with a 1 and 2 years.
The star, this asterisk is the convolution product, yeah.
Okay.
And this is composition.
That is composition.
Yeah. Which is why, yeah. The composition of, and remember, what is this? Epsilon sends you from your Hopf algebra to the field, and the unit sends you from the field to the Hopf algebra. And so this still takes you from the Hopf algebra to itself. Okay. So how are we gonna prove this? Well, what proof do we know like this? I mean, we said that this statement number 1 reminded us of the formula for the inverse of a product in a group, right? And so maybe what we should do is imitate that proof. So let me just, that's kind of motivation, right? Here's me thinking. So how do we prove in a group that GH inverse is H inverse G inverse? What we do is that we multiply them both by GH. So we say GH times H inverse G inverse is equal to, these two cancel, and I get 1. And actually, I can do this in different orders, and let me just do it in the same order as I plan to do it here. These two things are true by definition, and then you set them, well, and then what do? Then you say GH inverse is equal to GH inverse GH H inverse G inverse, right? Because this is 1. Because this is 1, these two are equal to each other. But because this is 1, these two are equal to each other. So that's how we do it for groups. Okay? And so presumably, what we should try to do is an analogous computation, but in this context of Hopf algebras. So that's what I'm going to do. I'm going to consider the following things. I'm going to consider multiplication. I'm going to consider the map S of H, S of G, and I'm going to consider the map S of GH. Okay? I want to prove that these two are equal to each other, and what I'm going to do is use this auxiliary one to do it. So I'm going to show that, just like I did over here, P star M is equal to the identity, and I'm going to show that M star N is equal to the identity. Okay? And then I'm going to make the same argument to conclude that P is equal to N. Okay? That's my plan. So to carry out that plan, by the way, as usual, I'm not justified in writing this down until I say something about it. So really what I should be saying about this is, let me define M of G comma H to be GH, and then check that that's a bilinear map, and therefore it descends to the tensor product. That's how you always define these kinds of things. I'm exactly using the universal property. And I mean, as time goes on, you see I'm just writing it. And you guys, I'm glad you're thinking in the back of your mind, oh, he must be using the universal property, and I am. Every time I do something like this, it comes from the universal property. Okay? So let's compute this. Let's compute P star M. Okay? Now, first of all, what is even the input of P star M? Where does P star M live? P and M. Right. So you see, the input of P and of M is tensors. Okay? And we're doing the convolution product, and so we need to plug in a tensor in there. And of course, it's enough to do this computation for pure tensors, and then bilinearity is going to be true for everything. Okay. G tensor H. Thank you. Yeah, by the way, I'm going to do a computation that's a little bit long, and it's early in the morning, so I will appreciate your help. Make sure that I don't make any typos. Okay, so what is this? Well, the convolution product is you're supposed to take the coproduct of this thing, and then apply P to the first, and apply M to the second. Okay, that's what I'm supposed to do. Okay. So what is this? Let me claim that this is the following thing. And I'll need to justify why that is. I claim that doing the coproduct over G tensor H is the same as doing the coproduct over G and doing the coproduct over H. And then doing this, doing P of G1 tensor H1 and then doing M of G2 tensor H2. And as you're more used to Sweetler notation, you'll just see that this is true. But maybe we're not too used to it yet. So let's think about what just happened. By the way, in Sweetler notation, And I think the way that Schuyler writes it in the book, he just says, notice that G tensor H sub I is equal to G tensor I, sorry, G sub I tensor HI for I equals 1 and 2. Okay. But what does that actually mean? Because I told you you're not really supposed to think of this as a particular element, and so it's not even clear what this equation means. It's a very kind of like a physicist equation. It's kind of an informal equation, and let's think about what this actually means. Well, what's happening is this. Okay, so maybe again, let's kind of open up a little thought bubble to understand what just happened here. But then, as usual, when you write down the proof, you don't confess to having thought. You just knew. So what happens? The thing is that to make sense of the top term, we are taking the coproduct of G tensor H. Okay. Now, can I write this? Well, the thing is that this lives in the tensor product. And so I can't apply the coproduct of H. What I need to do is apply the coproduct of H tensor H, which really is delta tensor delta. And that's really what I'm doing here, because that's the coproduct of that algebra. And so by definition, the way that you do this, when you have a tensor product of maps, it's delta G tensor delta H. Okay? And so in the left-hand side, this looks like sum over G tensor H of G tensor H sub 1, G tensor H sub 2. And what's this? The coproduct of G is sum over G. Let me go over here. This is equal to sum over G of G1 tensor G2 tensor sum over H of H1 tensor H2. Okay? And here you start to see what's happening. So the left-hand side is the sum over G tensor H of some things, and the right-hand side is sum over taking the coproduct over G and the coproduct over H, and then merging these two things together. Okay? So this is the same thing as saying sum over G and H, and then you take this tensor this, which is G1 tensor H1 tensor G2 tensor. And it is in this sense that we are writing this equation that this is equal to this, and this is equal to this. But that is not an equation that says that any particular element here is equal to any particular element here. What this says is that as we range over the coproduct of this guy, which decomposes into something tensor something, you might as well range over the coproduct of this one, and look at all the possible ways of taking something that arises like this and like this. Okay? And really, all that this equation is saying from here to here is that I take this equation and I apply P, M to it. Yeah?
So this is kind of silly, but we, not in practice, but sort of you got to get away with replacing the subscripts on the H with like 3 and 4. In other words, we're sort of disconnecting the G and the H is what we're saying. The H sub 1 isn't somehow related to the G sub 1.
So your question is whether it makes sense, or whether it might be clearer to put like a 3 and a 4 here instead of a 1 and a 2?
Actually,
or?
I'm not so much saying about the clarity, just whether or not that would be an accurate sort of interpretation of it, I guess. Would it be wrong?
I would not put a 3 and a 4 here, because that talks about going to the fourth tensor product, and whenever you have subscripts 1, 2, 3, and 4, you want to live in in H tensor H tensor H tensor H and take the third coproduct. So if you use subscripts 3 and 4, it should refer to taking the third coproduct and looking at the right two coordinates. So 1 prime, 2 prime might be a little bit less misleading, but I'm happier with this. So, but that answers it. Yeah. Okay. But so this is kind of the computation that is in the back of our heads when we go from here to here. Okay. And then we say, okay, well, I know what to do with this stuff. Because, I mean, in particular, one thing that you should realize is that I couldn't really say P of this because I don't have it in the form something tensor something, so I couldn't plug in. But now I can plug in P of something tensor something. I know what that is. Sum over G and H, and then P of G1 tensor H1 is just S of H1 G1, and M of G2 tensor H2 is just G2 H2. Did I do something wrong? P of G, oh yeah, sorry, P of G1 H1 is S of G1 H1. Thank you. So, yeah, this is really what I meant to write. And then, what can I do? Well, and maybe here, let me say because, so here the key thing was this, right? Delta tensor delta of G tensor H is the same thing as delta of G tensor delta of H. Okay, so this is the justification for this step. And now I'm going to want to do something similar, which is that I'm going to say, actually, this looks like a coproduct of GH. And I claim that that's exactly how it is. And at least they look similar. I hope this step looks similar to this one. So we're kind of undoing it, except that here we were doing it on the tensor product, and here we're doing it in the product.
So it's like in a diagram, since it's like you're going one direction using the trick, and you're doing something, you're going the other direction using the same trick.
Yeah. Now, what did I do here? Again, there needs to be some kind of justification of what just happened. So, I mean, I could write something like this also. GH sub I is equal to GI times HI for I equals 1 and 2. But I need to justify that because. So what's the because here? What's the equation that allows me to do this? The commultiplication is an algebra map. Here, I'm taking the commultiplication of GH. And here, I'm taking the commultiplication of G and the one of H. And so, really, what makes this step go is that the commultiplication of GH is equal to delta of G, delta of H. Okay? So actually, let me reevaluate what I told you, Seth. I think maybe it's not quite going around the arrows of the same diagram because this is just the definition of a tensor product. So here we're not really using anything, whereas here we actually are using that delta is an algebra map. And so here we actually need to use the fact that algebra and coalgebra get along. And again, if you just take this equation and you kind of do what I did here, then you'll see that you're able to do this. Okay? And this is where, Sweetler notation starts paying off. It's one of the examples where when you start getting used to this, actually, the computation is going to look shorter. Okay? And the more you practice with this, the less you have to justify things like this. Okay? Okay, so what should I do next? Do you guys recognize this expression that I just wrote? So that is this expression, right? Actually, this is just the convolution product of S and the identity at GH. It's just the convolution product S convolution I evaluated at GH. Okay? And that's good because that convolution product is just U epsilon of GH which is just the map 1 evaluated at G tensor H. And so what I have is that P convolution M is equal to 1. This U? So the convolution identity is 1, which is U epsilon. The U is sometimes omitted. And the reason is that U kind of takes the field into the algebra in a trivial way. So I wouldn't be surprised if on the notes I dropped it. Did I drop it? Is that what you're looking at?
Why do we get a tensor of the last one?
Where did this tensor come from? Maybe we can... Let's do it in a couple more steps. Let me drop the U because U is just embedding the field into just identifying the field into the scalars of my algebra. Okay? Now, epsilon is multiplicative. Why is that? Because this is supposed to be a bialgebra, so this part of the co-structure should be compatible with the algebra structure. Okay? And then I claim that this is the same thing as U, tensor U of epsilon. And why is this? Well, because if you look at this part, this is just epsilon G tensor epsilon H. But those are both scalars, right? Epsilon of G is a scalar, epsilon of H is a scalar. And so in the identification of K tensor K with K, let me do it a little bit more slowly. This is one of those equations that is a little bit bothersome, but we allow ourselves to write in Fiedler notation. Because here, these things live in different places, right? This lives in the field K, and this lives in K tensor K. So what this means is that actually we have this canonical identification between K and K tensor K, where the map is taking these two numbers and multiplying them. And so that's what I'm doing here. Yeah?
So in some sense, I feel like we're using a lot of equal signs where on some sort of structural level it's more isomorphisms or embedding maps applied to something like that, and we're just omitting a lot of that.
Yeah, maybe I didn't mention it in. Okay, so let me repeat the comment because on the microphone. So the comment is that a lot of these equal signs are they really equal signs? Like this one, for example. You know, these things, like I said, they don't even live in the same place in principle, and so how can they be equal? And the thing is that here we talked about having this canonical identification between K and K tensor K, where you take A tensor B to AB. This is an isomorphism. And so this equal is really saying that this is equal to this modulo the map that is here. Okay? And we tend to omit those just so that we don't have phis and cs and all kinds of things. And this is just one, I mean, as I said in the forum, this is a feature, just like Microsoft tries to say there are features and you're not very happy with them. This is a feature of Swidler notation. It's something to get used to, but the thing is that you're just kind of sacrificing precision to be able to manage expressions and move more quickly. Okay? And I think as you practice more with Swidler notation, you'll appreciate it. But even in the Homer problems, I ask you to prove things that actually don't have any right to be true, because I say, prove that this is equal to this, and the left-hand side lives in H, and the right-hand side lives in H tensor H tensor H. And so even the question there is, the equal is a kind of equal modulo these canonical identifications. So that's a feature. That's all. That's all I have to say in defense of that.
I can't help but ask whether or not you eventually consider Microsoft features to be like those things.
I worked at Microsoft for a year, actually. It's funny, so maybe I should be careful what I'm saying, especially on camera. But anyway, so what's this now? We agree this is epsilon, tensor epsilon of G tensor H. And then, again, here you can kind of put and the point is that this epsilon is the epsilon of the tensor product, right? This is the co-unit of the tensor product. And now let me just put the unit in front of it, which again is one of these kind of things that I allow myself to do because the unit just embeds the field into your Hopf algebra. And then now this is the U of the tensor product and composed with the epsilon of the tensor product, and that is the 1 of the tensor product under convolution. So this is what I call the 1, and maybe we'll actually write 1 of the tensor product under convolution. Okay. And again, as you have practice with this, you kind of see that this is equal to this, but then I'm glad that you stopped me, and I have to justify it, and I have to take my time. Maybe it'll take me a minute to see exactly what the steps are, but that's it. So that P star M is equal to 1. Okay? So that's 1/2 of what I wanted to claim. P star M is equal to 1. Any questions about this part of the computation? So this part is okay. This is good. Now let me compute the other half. You left me thinking about this. Let me tell you one feature of Microsoft that I like. Microsoft believes in pure research, and I think that's the only company that I know that does that. That's one very positive thing I have to say about them. I'll keep the rest to myself. Okay, so M star N, again, we need to evaluate it at G tensor H and see what we get. So this is the sum over the coproduct of this and this. Okay. And now I can do this a little bit faster, right? So now I know that this is the same as summing over G and H of M of G1 tensor H1 and of G2 tensor H2. And now I say what M is. So it's equal to the sum over G and H of, this is G1 H1, and this right here is S of H2 S of G2, right? So here I'm just kind of repeating what I did so far. Okay. Can you see something that I can do here? Yeah, all of those multiplications take place in the algebra.
So combine SH2 SG2.
I'm sorry?
Can we combine SH2 SG2?
So it's tempting, actually, it is tempting to combine them, and then you have to remember, well, S reverses them, but then the problem is that that's what we're proving, right? So eventually we'll know that we can do that, but right now we cannot, okay? If we could do that, then we could do the same thing as before, we'd be done. That's right. So if we forget about the G part, this is a sum over G, and then a sum over H. And so I could just say, I'm going to do it a little bit slowly. So this is a sum over G and a sum over H, so I can do G1 and then parentheses sum over H of H1 S of H2, and then S of G2. Okay, I just have to remember things aren't commutative here necessarily, so I have to keep things in the correct order. Okay. But then this right here, we know what it is. Okay, this is sum over G of, I mean, that's just the unit, right? So okay, G1, and then again, let me be a little bit loose and just call this epsilon of H. Okay, so that's the 1 of H, and then S of G2. Okay, and what can I do next? Am I allowed to take this out of here? I have to be careful with commutativity, but the thing is that epsilon of H is a scalar. And being a scalar, I can pull it out. And I get this, which is epsilon of G. Now, I would like to say this is 1 of G tensor H. Can I do that? Can I switch the G and the H? Again, they're still scalars, so I can do this. And then this is what we had earlier. So this is the 1 of G tensor H, sorry, of H tensor H of G tensor H. And that proves the other half of this. Okay. And then finally, if I'm going to justify that P and N are equal to each other, then I just have to compute the convolution product of P, M, and N in two ways, right? So if I say that this is 1, I'm going to get this is equal to N. But if I say that this is 1, I'm going to get that this is equal to P. And that's what I wanted to show. So that shows this property. And as I said, I mean, this has all the features of all the other ones, and so it would be good practice for you. It would be very good practice with field notation, for example, to prove this. And you'll see that it's, the proof is very similar. Okay. All right. Any questions or comments about any of this? Okay. So now you should always feel free to I mean, just remember how S interacts with both the product and the coproduct, and it does so very nicely, and with the unit and the co-unit. Okay. So let me leave this over here. And, yep.
I just had a realization regarding your lecture 12. There was a class in here at 11 that runs for an hour and a half. So I think the room is going to be occupied until 12:30.
So they let me reserve the room, but maybe. So there's a class from 11 to 12:30? Wait, so after this is the antipode. So 11 to 12:15? I don't know why they let me reserve this room then. Okay, so maybe what we'll do is this. 11 to 12:15. So this is more likely. Maybe this is more likely. So 12:30 to 2. And I'll double check and make sure that the room is free. And if it isn't free, then I'll email you guys and tell you what time it's going to be. And still, please come. Okay? Not at night. I can't ask you to come at night. I wouldn't do that to you. Okay, so let's see what else should we show about the antipode. Here's another nice proposition, which is that if a Hopf algebra is either commutative or cocommutative, then the antipode S has order 2. So if a Hopf algebra, I should say. So we have so it needs to exist, and if it does exist, then it has order 2. I guess it could also have order 1 if it's trivial. So this goes back to 2 points. So first of all, I mean, originally Seth asked if the antipode always had order 2, if S squared was the identity. And well, here you can see that first of all that in a lot of important cases this is true. Actually, I don't. Yeah, in all but one example that we've seen so far, this is true. And the one example that this does not apply to is the one example we've seen of something that is neither commutative nor cocommutative, which is this H4 algebra.
How can we have the antipode the order 1?
That's just if it's the identity.
Oh.
Yeah. So that's kind of a silly example. Really, I mean, really, it's order 2 unless everything is pretty trivial. But this, I mean, this shows why it took a while to find examples where the antipode did not have order 2, because it took a little while to find Hopf algebras that were not commutative and not cocommutative. So let's suppose that H is commutative. Okay. So what I'm going to do, I need that the composition of S with itself is the identity. And again, here you have to be a little bit careful. You know, what order, what identity. But here we're saying that S of S is the identity as composition. Okay. So here, this is not convolution. This is composition, and this is the identity function. Okay. And so what I'm going to do is that I'm going to one property of the identity function is that it's the inverse of the antipode in the convolution product. Okay? And so what I'm going to do is that I'm going to show that this is the inverse of the antipode. Okay? So I'm going to take this thing and take the convolution product with S, and that's going to give me 1. Okay, so that's my claim. And then from this, I'm going to be able to get that this is the identity, because the identity is the one that satisfies this equation. Okay, and so let's compute this. So I compute this. Okay. What do I need to plug in here? S is going from H to H. And the composition of S with itself is also going from H to H. And so the convolution product also goes from H to H. And I don't plug in a tensor as I did earlier. I plug in a single element. Okay? And then I say what this is. Sum over H of S of H1 S of H2. Okay? That's the definition. And then we write S of S like this. Okay? And now I'm going to take your suggestion, Brian, that I know what S of something times S of something is. S is anti-multiplicative, so I get this. Right? What should I do next? Well, this is commutative, so I can switch these two things, which is good. You should kind of like the ones on the left and the twos on the right. I hope that's an instinct that you have by now. Okay. And so here we're lucky enough that we can do that. Because Hopf algebra is commutative. Okay. Now what can I do? Well, S is a linear function, which means that being a linear function, I can pull it out. So I can pull it out of the sum, and I get this. Right? Yep. From here to here? From here to here?
Do you mean like an S
No, so here what I'm using is that S of this times S of this is equal to S of this times this, but it's in the opposite order.
Oh, I was looking at it the other way.
So I'm using this.
All right, gotcha.
Oh yeah, so it's this but backwards. Okay. Now we know what this is, right? This is again the convolution product of S and I. So this is S of the 1, which is U epsilon of H. But what's this? Well, SU is U. So we just get U epsilon of H, which is 1. Okay. So it is. So that equation is true. This equation is true. And again, using that equation, I can make the same kind of computation that if I compute this, convolution S, convolution identity, then if I say that this is the one of the convolution product, I get I. But if I say that this is the one of the convolution product, I get this. Okay. So that proves it in the case that my Hopf algebra is commutative. Okay. Okay. Any questions about that computation? So now let's try to do the same thing if H is cocommutative. So if H is cocommutative, where does this argument break down? This is the trouble spot right here. This is where we have to be careful. That step is not valid if we don't know that the Hopf algebra is commutative. So, can you think of something else we could do? So let me, I'm missing a parenthesis here. So, okay, so let's go down and make, so okay, I'm just doing something here, claiming this, and let's just follow this computation and see, and so from here to here, same thing, that's true. From here to here, still true. This is not true, okay? So let's think of something different to do here. So this is not a good step. It is true that I can pull out the S, because S is linear. Now this is not true. No reason for this to be true, because these guys don't commute. So what can I do? I haven't used that as cocommutative, and so how can I use that? So I don't quite want to insert a tensor because this, I mean, this is a product. This is an H, and I'm really multiplying them. And if I put a tensor, I'm going to be computing something totally different, which is the tensor product. But why do you want the tensor product there? Cocommutativity says something about that side. So what does cocommutativity allow me to do? Well, what's that? Can I just switch the 1 and the 2? That's exactly what cocommutativity allows you to do. Right? Cocommutativity says that the sum of H1 tensor H2 is the same as the sum of H2 tensor H1. And then you can apply any function on the left, and that's still going to be true. And that means whenever you have something like this, it's a function of H tensor H, and cocommutativity tells you can swap the indices around. So you can just change 1s for 2s, 2s for 1s. So here, now this is a valid step. It's a little bit different from the previous one. And it is using cocommutativity.
If you were to define cocommutativity, would you say delta H1 H2 equals delta H2 H1?
Let's write it down so that we remember what cocommutativity was supposed to be. So first of all, cocommutativity, is it this? It's not this because you're applying delta to a tensor, and you're supposed to apply delta to a single thing. Really, what cocommutativity says is that if you do this, then you can apply the twist map, and that's not going to change delta. In other words, this is the same thing as in Sweetler notation. Cocommutativity says this. It exactly says that you can swap the indices 1 and 2. And then what I was saying is that if you apply a function on the left, you can apply it here and here, and then whatever you get in Sweetler notation here, you just swap the 1 and the 2, and you get the Sweetler notation for this. So really, you can almost think of cocommutativity as the definition of that being that you're allowed to do this that I did here. That's the definition. And then the rest works, right? The rest works because this summation right here is, well, I just erased it. I had it written over there. This is the convolution product of identity convolution S. Identity convolution S is 1, which is U epsilon, and the rest of the argument works in the same way. Okay. So you see, cocommutativity is a lot like commutativity. You're allowed to swap things around. You just have to be careful when you do it. You can't swap in a multiplication, but you can swap in a co-multiplication. But in effect, it allows you to do, at least in this case, it allows you to do exactly the same thing. Okay. Cool. So that means that for a lot of Hopf algebras, the question of finding the order of the antipode is going to be immediate as soon as you know that it's commutative or co-commutative. Okay. Let me make a couple more comments about the order of the antipode. So let me make another proposition, which is that no antipode can have odd order. Except order 1. You cannot have odd order bigger than 1. Okay. And the proof of this actually is pretty easy. Suppose that you did. Let's say that the order is 2k plus 1. So then, what is S 2k plus 1 of gh. Well, when you apply s, it swaps the order of the product. If you apply s again, it swaps it again to the right order. If you apply s again, it swaps it to the wrong order. If you swap it again, it swaps it to the right order. Okay? And so if you apply it an odd number of times, you get this. It's pretty straightforward by induction. Really, what I'm doing is iterating this 2k plus 1 times. Okay? But this is supposed to be the identity, so this is GH, this is HG. Okay? Well, so I'm not assuming that I'm commutative, but I just proved that it's commutative. Right? I assume that you have odd order, and what I proved is that H is commutative. But if it's commutative, then S has order less than or equal to 2, which is a contradiction. Are you happy? Does it bother you? Or? It's good, right? Yeah, so very nice and easy. Let me then conclude by making a couple of comments. So I think I mentioned this last time. Well, yeah, so I mentioned it last time that there are Hopf algebras of order 1, 2, 4, 6, 8, etc., and infinite order. And this is something you're going to prove in your homework. So this completely settles the question of what the orders of Hopf algebras can be. There are Hopf algebras with antipode order any of these things. Okay? Let me mention a conjecture that is open to this day. It's pretty intriguing. It's one of a series of conjectures of Kaplansky that really drove the field forward. He conjectures that the antipode of any finite dimensional Hopf algebra has finite order. So if H is finite dimensional, then the antipode has finite order. This question was wide open for a long time. And now it's not wide open, but it's still open. The reason I say it's not wide open is that I'm not sure exactly when this conjecture is from, but in '88, it was shown to be true in characteristic 0. So theorem, this is true as long as the characteristic of the field you're working with is 0. This is a theorem of Larson and Bradford in '88. But somehow, if the characteristic of K is P, some prime, then we don't know if this is true or not. It's wide open. Maybe you can solve it for the project of the class. I think it could be an interesting question to just look into, see what people have done to try to do this. What Larson and Bradford did, why it breaks down in characteristic P. But that's the current status of this question. Okay. I think that's a good place to stop, and so we will continue hopefully at 12:30.